Welcome back. So, in this afternoon, Shubhabrata Das of Presidency University. So, he'll be speaking on small cancellation theory. Shubhabrata, it is over to you.
Okay, thank you. So, small cancellation theory is a is an old enough subject. Now, it did not start as something like a part of geometry group theory. It's much older than what is known to be geometry group theory today. So, we will be talking about some aspects of it, mostly definitions and a few examples and some basic properties today. So, let's get started. So, uh, one correction here is curvature formula mentioned here, but probably today we won't see curvature formula. May or may not. So, what small cancellation theory is essentially, it dates back to almost a century, maybe more than a century. Works of Max Den, mostly on the decision problems, and he was working on the presentation of surface group, fundamental group of closed surfaces, and there he saw that if some word is trivial, then there are some parts of the sub, there are some subwords which are parts of some conjugate of a relator where it is more than half of the relator, the length of those subwords. So what he essentially did is he replaced those subwords with the remaining part of the relators, essentially shortening the entire word, which he started with, which was trivial, and it is famously known as Den's algorithm, which we will be talking about later, maybe tomorrow. What it does is it reduces the presentation and finally giving us a way to determine whether a word is trivial or not. It gives us an algorithm. So starting from something which bounds a disk maybe. Now, in a different form, what is the main problem that this small cancellation theory tries to address is, suppose we start with a group G and we have subgroups R1, R2, Rn in G. So this is a study of finding conditions on essentially these subgroups R1, R2, Rn, such that we can understand this normal subgroup generated by these subgroups better. One of the aims, and the other thing is to understand the quotient group, quotient of G by the normalizer of these subgroups. So what is it really trying to say? Suppose we start with a finitely presented group G. I hope we all are familiar with presentation of a group. So suppose we have a group G which has a finite presentation like this in terms of a generating set S and a set of relators 1 to R1 to Rk. In that case, we are essentially trying, under small cancellation theory, we are essentially trying to find conditions on these relators R1 to Rk. See, if we have to compare, if we have to relate this statement in this context for a finitely presented group G, what does this statement mean? That we are trying to find conditions on subgroups. Which subgroups? So subgroups in this context are the cyclic subgroups of the relators, finitely many relators that we have. And the quotient group that we want to look at is the group G. And the group G we have started with is the free group on these generating elements. So the classical small cancellation theory, which started mainly from Den's work, and then many other people proved many other results. So that deals with a free group generated with finitely many elements S, and finding conditions or giving conditions on suitable finite subsets of elements which are the relators, so that we can say nice things about the quotient group Fs quotiented by this normal closure, the normal subgroup generated by all these cyclic groups Ri's. So what kind of conclusions are we looking for in here? What these conditions are essentially asking is that any common subword between two relators has to be small compared to the length of the relators. So two relators will overlap on the edges, on the boundaries, if we can think of the relators as something like a disk, and the boundary of the disk reads like the label of the boundary that reads like the relator, the given relator, then in the Cayley complex, two of these disks will overlap on their boundary levels. So what we are essentially asking for is that whenever these things are overlapping, the boundaries of these disks, we will have some common subword on the boundary level. And those common subwords, what happens if the common subwords, the length of the common subwords essentially, are small compared to the length of the entire boundary level. So the study of this question and the consequences is essentially small cancellation theory. Why cancellation? Because when two such boundary levels overlap, then there is a cancellation involved. Because we will see the right definitions in a moment. So, Abhijita, is there any way to write or share more screen?
Share screen. Okay, so if you type on the share screen,
I already have. Okay, I can share a new screen. Is it?
whiteboard, can you share?
Let me see if I.
But your previous screen is gone.
I have already shared one thing, but if I so is the previous slide gone?
Yes, now it is gone, but the new one came.
Oh, okay, okay. So I cannot share more than one, it seems. Okay. Okay. So how can I write some things if needed?
But this option is not there. Annotate. It's not here.
Yeah. So suppose I want to scribble something alongside. Is there a way to do that?
Uh, just one minute.
Just one more.
No, right now you can't do it. So if opening a big,
Okay. 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 I will do one thing. Uh, I will.
so maybe if you have
So
two pages,
can you see
right. Yeah.
this thing now? Okay. You can see this.
Yes.
Okay. Okay. So so essentially, what we are talking about is those common subwords which we will be calling a piece. Uh, they will be subwords which appear in two different ways. What exactly it says is that it is a subword u such that there exist cyclic conjugates of relators. It could be the different cyclic conjugates of the same relator. It is not necessary that this, what it essentially means is, suppose this is a relator, this is the diagram of a relator, say R1, and this is R2, and the two diagrams, we will come to the notions of diagram, what we really mean by a diagram and so on. But intuitively, in the Cayley complex, we can think of these two relators being giving two-dimensional disks, and these two-dimensional disks will overlap if they have a common subword like this. So these parts we are essentially calling a piece. These relators are not needed to be distinct necessarily. They can be the same relators, but different cyclic permutations of the same relator. In that case, we will call this common segment, the subword, to be a piece. And the C prime 1/6 small cancellation condition, SCC stand for the small cancellation condition. This is the most commonly known small cancellation condition. What it demands is that the length of this subword u has to be less than 1/6 of both of these relators. Length of u has to be less than 1/6 of both of these relators. It doesn't seem to be such an interesting condition, but it has really many interesting consequences. So here there is nothing special about 1/6, but as such, but this is kind of the threshold beyond which the hyperbolic behavior starts displaying. What I mean essentially is, if I replace 1/6 by any other lambda, and lambda is less than 1/6, then we will see that a C prime lambda group will be hyperbolic. I understand that in this workshop we have seen many results regarding hyperbolic groups. So this is one addition in the class of hyperbolic groups. The small cancellation groups C for C prime lambda, where lambda is less than 1/6. We will see the proof of this fact. And this fact and other results have many other consequences, like a few of these mentioned here. So this is just a brief introduction that what we are essentially up to, what we are trying to do in this mini course. We will discuss mostly the classical definitions in small cancellation theory and some of the generalizations with a few very remarkable applications. Fine. So the basic definitions, we take G to have this presentation, S be the generating set, and R is the set of relators. What we mean by that is S is a symmetric generating set. That is, we have all the generating letters with their inverses, and we have this mapping. So G is essentially a quotient of the free group generated with these generating elements. So we have this quotient map from the free group on S to G, and the kernel of this quotient map is the normal subgroup, which is generated by these set of relators. So R is the set of relators. This is the normal subgroup generated by R. So G is isomorphic to the free group modulo, free group on S modulo this normal subgroup. So a word in this free group is a finite string of letters. Essentially, we will restrict ourselves to a finite presentation in almost all the cases that we will be looking at. That is, both S and R are finite. And now a word W in FS is a finite string of letters, SI in capital S. So W will be something like S1, S2, Sn. And the length of W will be the number of letters in W. So W is just like a path. Okay. And here we are essentially considering the reduced word W and counting the number of letters in that. So what we mean by reduced word is essentially the freely reduced word, and that is, it does not have any subword of the form SS inverse or S inverse S, so that we call freely reduced word. And R is a relator if it is an element of capital R. R is cyclically reduced if a cyclic permutation of R is reduced. What I mean by that is, if I view R, so if I view R as a circle, which is sort of bounding this disk, I can see R as the boundary level of this disk, and it may so happen that if I write R as some word, say S1 to the K1 up to S n to the K and something like that, these Ki's are integers. It may so happen that there are no subword of this form SS inverse or S inverse S in this word, but there are elements in the beginning and the end, so that if we form a circle like this, a loop like this, then there are cancellations at the end. So there are possibilities of having cancellations at the end if we have inverse words in the beginning and the end. So if we do not have such possibilities, we call them cyclically reduced. So we essentially assume our collection R to be a collection of cyclically reduced words. So R is called symmetrized if all elements in R are cyclically reduced and all distinct cyclic permutations of R and R inverse are present in capital R. So the capital R, which is the collection of relators, just like we take a symmetrized generating set, a symmetric generating set, we consider the inverse letters for all our generating letters. Similarly, we consider a symmetrized set of relators where we have all the distinct cyclically reduced cyclic permutations of our relators and their inverses. So a word U is called a piece. A word in these generating elements is called a piece relative to this collection R, this symmetrized collection R, if there are two distinct elements in that collection, R1 and R2. These collections are not necessary to be, these elements are not necessary to be distinct, but these elements are needed to be distinct, the V1s and V2s. So that means U figures in two distinct ways. U, the subword U, figures in two distinct relators in distinct ways. The subword is same, but it is present in two distinct ways in the relators. And that implies when I take the relators and their conjugates and relators and their inverses and their conjugates and take products of them, in that case, there can be cancellations, possible cancellations among the relators and their cyclic permutations. So a piece is a subword which gives us such cancellations when we are taking product of elements from R essentially.
So one question.
Okay. Yeah.
Yes,
Hello,
can you
sir.
just give an example of art where it is symmetrized?
Sorry?
Give example of art
Yes.
which is symmetrized.
Which is symmetrized?
Yes, I mean, so give a presentation of group. So
Yes.
art is symmetrized.
So you take a relator and then take all its distinct cyclic permutations.
Yeah, yeah. For example, if I take A, B, A inverse, B inverse, just
Yes.
Z cross Z.
Yes.
So it is it.
So in that case, if you start from, you're taking A, B, A inverse, B inverse. If you take a cyclic permutation, then you can start from B, right?
Hmm.
B, A inverse, B inverse, A, something like that.
Okay. So you're taking all the cyclic
Cyclic permutations of that.
Okay. Yeah.
Okay. So
So
see,
what is
essentially,
Hello, sir.
yes,
Hello.
yes.
Sir, could you please repeat the what is cyclic permutation is cyclically reduced? I mean, with it possible
Okay,
something.
okay.
Yeah.
So what I meant is, if I write this is a relator, right? R is a relator, and if I write the relator, suppose I take the relator, take a word, say A, B, A inverse, B inverse, A inverse. Okay. Suppose this is my relator. In that case, you see there are no subwords in this relator like this, right? So this is a freely reduced word,
Yes, sir. Okay.
but
After. getting permuted, cyclically permuted, so it will be not may not
Yeah,
be deduced.
yes. So
Okay.
so here you can have A and here you can have A inverse, which can
Yes.
get cancelled, right?
Yes, sir.
Okay.
Okay, sir.
Yes.
Got it.
So
Yeah.
I have one
Any
question. To define
yes.
piece, why I need my set R to be symmetries?
Sorry.
To define this piece definition, why I want my
Yes.
R to be symmetrized? My
See,
idea is to
it
see the cancellation pair only.
yeah. So you see that if I sorry, I do not have space here. So suppose I look at the Cayley graph of z square. So in that case, this is A B A inverse B inverse, right? Right?
Yes.
Yeah. So if I only write A B A inverse B inverse, how am I going to? So here there is a cancellation. Do we see that? On this edge, so this is R1 and this is R2. Though we have two different, two distinct cyclic permutations of the same relator. So here it is AB A inverse B inverse. I am having a common subword which is B, right?
Yes.
If I write it in this way, so you consider R1 inverse. What will be that? V1 inverse U inverse, right? Now if you form this product, say R1 inverse R2, then you have this, right? V1 inverse U V2, and that is V1 inverse V2, isn't it? Is it okay?
Yeah, okay, but
But you see, here B is appearing in this the way we had written. So it was A, B, A inverse, B inverse, right? So for this word, it is A, B, A inverse, B inverse. So we are looking at the B inverse subword here, right?
Maybe you can write down R1 and R2. Then it will be clear, I guess, for the example.
Yeah.
R1,
So maybe write down here. So it will be R1 will be, say, B B A inverse B inverse A, right? So B A inverse B inverse A. Is that okay?
Yes.
If I start from this point, right? And if I look at this relator, this loop from the same point, then I will look at it as, say, I look at it as B,
A,
then A, B, A, then this is B inverse, and this is again, this was A, so this is A inverse, right? Sorry,
yeah,
did I make a mistake? Is it okay? Did I make a mistake?
no, it's okay.
It's fine.
No, it's okay. It's okay. Yeah, yeah. Right. Yeah. So now you see that if I take a product of this form, then this B gets cancelled, right? And what we are left with is this word, and that is, if I write it here, it is A squared be a to the minus 2 b to the minus 1, right? So we form a product which is again another loop in this complex, but we obtained it via this cancellation. Is that fine?
Yeah, understood.
We had only one relator here, but we wrote it in two distinct ways so that we can form the product like this. Okay, so shall we continue? Any other question?
Please continue.
Okay. Okay, so that is what we are calling a piece. Now we want to see some geometric way of representing our relators or words, which essentially words in the group. So what we can observe is that most calligraphs are not embeddable in art, right? But if we can see that if we have an element omega from the normalizer, from the normal subgroup generated by these relators, there is a finite planar diagram giving omega. A finite planar diagram is like a 2 complex. Okay, just like this, we can see one here. So you see omega, say W, was an element from the normal closure of R, right? So what is that? It is the collection of, say, all products of conjugates of elements from R, right? So if we think of this rectangle here, what we have is one element from R. So this is our relator, and a product with that. So this is my base point. So suppose this is the base point, 0, 0. And from here, I will take this element, group element A, and then trace the relator again and come back to the base point. So it is like R product G R G inverse, right? So this is an element here, right? So we can see clearly in this case that we have an element omega given by the boundary level of this planar region, this union of these two squares, and the boundary word reads like this, right? And this is clearly a product of conjugates of the generating of the relator. This is a one relator group. So is a this is a phenomena that can be stated, that can be have in much more generality. This is something devised by Van Kampen in the early 20th century, and then Linden rediscovered it, possibly unaware of Van Kampen's result, much later. And Linden and Schub and Grindlinger, and so these are the pioneers of classical small cancellation theory, which sort of revived after many years after Max Den and Van Kampen's early works. So anyway, Van Kampen diagram of a freely reduced relator. Freely reduced, we understand what? Van Kampen diagram of a freely reduced relator W over a presentation G is a finite finite pointed, I mean, it has finitely many vertices, edges, everything. Two-dimensional CW complex M, a boundary path of that two-dimensional complex M, and a labeling function, a function which assigns labels to all the edges. So a Van Kampen diagram is essentially a triple like that. And what it says is this two-dimensional complex is homeomorphic to a simply connected closed subset of R2. To each edge of M, this complex, this function f assigns a letter from the generating sets. And by x inverse, we mean the inverse edge with the opposite orientation. So f assigns the inverse element, inverse level to the inverse edge. F assigns the inverse element to the opposite edge. So that is quite expected. The label of every simple boundary path of a two cell of M is an element of R star. So what is that? And R star is R for us, right? R star is the symmetrized set of R, and that is, we have taken R to be symmetrized, so that is equal to R. So the level of every simple boundary path of a two cell of M is an element of R star. So it is essentially a cyclic permutation. That is what we want, right? And the boundary path P, the boundary of the entire two complex M. So the boundary path P that starts and ends at the base point, and it is the given freely reduced word W. Okay, so that is it. Essentially, what we have drawn here. So it is saying this diagram will be a simply connected subset of R2 like this. Each edge correspond to a generating element, its label, and the level of a simple boundary path of a two cell of this M is, so it's kind of obtained by gluing these two cells, right? So just like this, we had two cells here coming from the relators, and these two cells joined along this edge is giving us a diagram M, okay, corresponding to a freely reduced relator, which is this. Okay, so that's what that means omega is coming from this. Okay, so sorry, W is coming from this. So that is what we call a Van Kampen diagram. And how to construct these diagrams? These diagrams are very helpful because we are looking at this geometric way of looking at the presentation and looking at cancellations, the length of the subwords along which it's getting cancelled and so on. So we will use this diagram. So we need to know how we obtain these diagrams. So what we can do is omega is a non-empty freely reduced relator of this. That means it's an element here, right? So elements from the normal subgroup generated by R, and elements in the normal subgroup generated by R, they look like this, right? So and since omega belongs to that normal subgroup, omega is freely equivalent, right? So omega may not exactly look like the product because there could be a lot of cancellation. There are almost necessarily a lot of cancellations involved here. And so we can think of omega freely equivalent to something like this wedge of balloons, right? These are like balloons and these are like strings. So we have, say, k many balloons here, right? So we have k balloons wedged at one point, and these are essentially GIs and GI inverses. So R1. So this is G1, R1, G1 inverse, G2, R2, G2 inverse, and so on. So GI, RI, GI inverses are freely reduced, but omega prime, it is not in general, right? So now omega prime gives us a 2 complex. This is also a 2 complex, I mean, in the strict sense of the word. And the boundary of this 2 complex is P prime. So this 2 complex, let's call M prime, and the boundary of this 2 complex is P prime. And we can read the boundary like we can start from this base point, we can go along this, travel this, come back, again travel this, go around this and come back, and so on. And that will give us a 2 complex. And these are like disks joined with the rest of the 2 complex by just a thread. We will essentially reduce them, but this is the diagram. We want some diagram like this obtained from this. So after all the reductions that we can possibly do, this will be the final diagram, sort of. So what we do is, yeah.
One question. So this
Yeah.
RIs,
RIs.
so there can be identification on the at the boundary, right?
Of boundary of RIs, you mean?
Boundary of
So RIs are also giving us 2 cells, right? Just like this. You mean the boundaries of RIs,
so,
right?
yeah.
Yeah, of course. And definitely we will have.
So suppose this X and X inverse comes in RI, so they will be identified in a complex that you are saying?
X and X inverse are coming in RI.
So
I didn't understand.
oh, okay. So maybe X and X, they are.
So you are saying that 2 X's are appearing in 2 different places?
No, one RI itself. Let us take
Yes.
the presentation. A and A square is equal to 1. R is A square, right?
Okay.
So R is what? Just A square, right?
Okay.
So what will be the complex corresponding to that?
So we are not finding a complex corresponding to the presentation, right? We are
Only one word, A square.
okay. So it is already reduced 2 cell, right? If you have that, suppose A square is your, so we will just have a diagram like this. Sorry. Just take a disk, which looks like this. Say this. In your group, A square is 1, right?
Correct.
So it will be something like this.
But what will be the complex?
What complex? So this is the 2 complex. This is a 2 complex corresponding to an element from the normal subgroup generated, right? So you have given me the element A square. So this is the 2 complex corresponding to A square.
No, how you are attaching the disk to this boundary?
Sorry? We already have disks corresponding to relators, right?
Okay.
So these are disks, R1, R2, R3, RK. These are all disks. So what we are doing here is, this is a contractible thing, of course.
Okay, all right. You are not identifying anything, right?
No. I am starting with all these balloons, and balloons means not exactly balloon. These are disks. It looks like balloons. These are all disks. So there will be heavy cancellations because we are going the same way and coming back. So there will be heavy cancellations, and essentially we will get some picture like this. That's what the diagrams are.
So can you see some example for easy?
Yes. Yeah, see, I can give you examples right away if you want, like this.
So for this Z cross Z, I think this will be easy.
Yeah, Z cross. Okay, fine. If you want to see examples for more complicated groups, suppose I take.
I think you can add a page here. There, then you'll have more.
I add a. If I add a page, will it come at the end? So then I have to go back and forth.
Okay, okay.
So yeah. So suppose I have a relator, say for a surface group, a genus 2 surface group. Say something like this, and suppose I have another added to this side. Okay, some other. Say it's difficult to draw octagon like this, so I am not drawing an octagon. I'm just drawing a disk here. Okay, so suppose this is the base point. Okay, so if I trace this is a disk, right? Essentially, so if I trace this is a disk, and if I trace this is also a disk.
Yes.
So what I am getting here is essentially R1, R2 for two different cyclic permutations, right? And you can see that there is some cancellation happening here.
Yes.
Right? So whenever we are gluing two such disks, two cells, there is some cancellation because of the cancellation we can glue them there. That's the common subword along which we are gluing them, right?
So
So
if I have a
this,
common subword, I am gluing along that one.
yes, I have to find something like that, right? Otherwise, how can I glue?
Okay. Okay.
So this picture, this is a very simplistic picture, a bad picture. So this is just like R1, R2. But I mean, why I was going to this picture, it is easier to draw here. Suppose this is the base point. Maybe I'll draw something here. Suppose this is the base point, okay, and suppose we look at this. So this is a too complex, right?
Yes.
Now I have only one relator here and different permutations of that, right? So how can I get this two-dimensional region in R2? And what does it correspond to? So it essentially corresponds to a square b a to the minus 1, b a to the minus 1, then b to the minus 2, right?
Yes. Yes.
So a square b a to the minus 1, b a to the minus 1, then b to the minus 2, right?
Yes. Yes.
You see that we have two positive b's, we have two negative b's, we have two positive a's, we have two negative a's,
Mm-hmm.
and then we are back to the starting point,
Yes.
right?
Right.
Right. So, but how are we getting this? This is something like my W, what I start with. But that W, since I know that it is trivial, I know that it's trivial, right? So I know that it comes from the normal subgroup generated by this. And that means it must be a product like this,
Okay.
right? And so which product is this? I can choose my GIs. Choice of GIs are not strict, but suppose I can go this way. I will go here, I'll go to G. So this is my G, suppose, to start with this one.
Yes.
So this is R1, suppose, for me. So it's like G, R1, G inverse. What I do is I go along this path. This is G, G1, say, G1, R1, G1 inverse. So I go along G, I travel R1, and then I come back along G1, right? So this is a conjugate. Just this is like the balloon, okay? This is like this R1 balloon. G1, R1, G1 inverse, right? And then
Yes.
I will have to go to this one. How will I go there? So I will take this path, G1, right? So G1, and I cannot stop here. I have to go till here to access this, right? So I take this path. This is G2, and G2, you see that it is just like G1A. G2 is G1A, right?
Right. Right. Yes.
Right? So G2 is G1A. Then I go along this relator. Let's call it R2. It's the same thing, but let's call it R2. So I go along G2, I travel R2, and then I come back along G2, right? So I take a product of that. So G2, R2, G2 inverse. Now you observe that I had G1 inverse while coming back from the first one. So I had G1 inverse. And then I have G2, where G2 is nothing but G1A, right? So there
Right.
is a
Right.
heavy cancellation here. G1 inverse, G1 gets cancelled. I have only A remaining, right?
Yes. Yes.
And that A is giving me this A. You understand? Here, that A square is A dot A. So that
Hmm.
first A has come from this cancellation essentially,
Yes. Yes.
because the other part will also be cancelled.
Hmm.
You understand? So finally, in this way, if I take a product, I will take product of this also, and there will be G3 inverse, and all those things after getting cancelled, we will have this thing remaining, the boundary of this figure. Okay. So this thing I am essentially calling the wedge of balloons. And then after all these simplifications between these conjugates, we get this thing. Okay, is fine. So what we are saying here is, if omega is an element from that normal subgroup, then omega prime is something which it is freely equivalent to. And if that freely equivalent thing is already reduced, right, it can be reduced. So something like this. This is already a reduced thing, right? So we don't have to do anything. So then it itself is a diagram, right? So this itself is a diagram that is satisfying all these properties you can observe. So if it is not, then we will reduce it by this thing, what we were doing essentially. Okay, one thing I forgot. So essentially what I am following as a reference is the book by Linden and Shoup, called Combinatorial Group Theory, and the chapter 5, fifth chapter, is called Small Cancellation Theory. And also there is a book by Gis and Dullahar. So that is on Gromov hyperbolic groups, and there is an appendix to that book by Ralph Strebel, and that is on small cancellation groups. I'm following that as well. And there are other references here and there. I will give all the references maybe at the end. So these are two primary references that I'll be following. So we are essentially reducing the wedge of balloons like this. This is what I have just described with this Z2 product is written here. So finally we will get something like this two-dimensional complex, and that the boundary will read W. The boundary of that two-dimensional complex will read W, which is this in this case. Fine, very good. So now let us come back to the definition of all these small cancellation conditions, and the most important of them is the metric. This is called the metric small cancellation condition, C prime lambda, and the C prime lambda says for lambda greater than 0. You see lambda greater than 0, but lambda greater than or equal to 1 doesn't make any sense, right? So if lambda is greater than or equal to 1, then what does that mean? That length of the piece, length of the subword u is less than, say, lambda is 2, then 2 times the length of the relator. So we know that in any case, the length of the subword is less than the length of the relator in which it figures, right? So that is redundant. So we write lambda greater than 0, but mostly we are interested in lambdas less than 1. So, and most importantly, less than 1/6, less than or equal to 1/6. So what is C prime lambda? C prime lambda is a presentation like this SR, where any piece that we have defined what a piece is. Now, if we have a piece W, then that has to be less than lambda times the length of R. Now, let us see here. This is the relator, just like this picture. It is exactly the same picture, right? So we wanted two tiles from the tiling of the hyperbolic plane by the fundamental domains of pi 1 sigma 2. That's the fundamental group of genus 2 surface, and this is the relator, right? So now you can see in this picture, this is a better picture than that. So you can see in this picture that if two such octagons have to overlap anywhere on their boundary, then it has to be along an edge and not more than that, right? So you can see here, if you also remember the presentation, that it is the group generated by with this, right? With all the inverse elements as well. So this is the relator, and this is the relator, right? So here you can see that if these, it's a one relator group, and the entire tiling that we get of the plane, that is by this octagon, by repeating this octagon infinitely many times. So where should the tiles, fit together? On the boundary, and at most along an edge they can fit together. That means they have at most an edge common, right? So if we remember our definition of a piece, see, a piece in this case is just this. Or if you have another octagon sitting here, then a piece is just this, right? If you have another octagon sitting here, then just this much is a piece. Now, how much is the length of that piece compared to the length of the relator? You see here we have only one relator, and the length of that is 8, right? Length of the relator is 8, and the length of the piece here is 1. So what can I say for this situation? What is the lambda that I can get? What is the lambda that I can get here? Anyone? So we can see that the lambda, the length of the piece has to be less than that. We can see that in this case, length of the piece is equal to 1/8 of the length of the relator, right? Because we have 8 edges and the piece is 1 edge at most, right? So it is equal to 1/8. So we can write it as, say, this, right? So we can see that this is a 1/7 group, that is, this group satisfies C prime 1/7. It is of course not necessary to take lambda to be an integer, but lambda to be 1 upon an integer, positive integer, but we are you can say anything say greater than 1/8 will suffice here, but we are considering an integer 7, so it's a C prime 1/7 group. So I hope by now these things are clear more or less. Now the C prime lambda condition. Now there are two other conditions, the cancellation conditions that we will be discussing. So one is called CP. It's more of a combinatorial condition. So what does it say? It says that if you have a presentation like this SR, then CP presentation satisfies the condition CP if no element from that symmetrized set of relators are, if no element is a product of less than p pieces. Okay, what it says is that if no element in R is a product of less than p pieces, it has to be a product of at least p pieces, no less than p. You see that here in this case we were having all the pieces having equal length. That may not be the case always. Even here in the Z2 situation, we had pieces of equal length. What were the pieces in the Z2 situation? Can anyone say? What were the pieces in the Z2 situation? They are just the generating elements, right? So even there, the pieces were 1/4 of the relator, right? So here they are 1/8 of the relators. So if you want to write down this relator, it will be, you will need say 8 pieces, right? How many pieces do you need? You cannot write it as a product of say 7 pieces, this relator or any other cyclic permutation of that. You cannot write it as a product of 7 pieces. So you need at least 8. That is what it says, that a presentation SR is said to be satisfying CP if the if the relators from this R is a product of no less than p pieces. Okay, and what does that mean pictorially? You see that here I have written something which I will come to after a while, but I have written this statement just to illustrate in terms of picture what it should mean, that when I'm saying that a relator from R should not be product of less than p pieces. Suppose I have a presentation SR which is CP, and I have a diagram for say some omega, and I have an interior face like this, which is a relator. So say an interior face which is giving me a relator R. Now this relator is bordering, it is bordering with many other relators, right? So this one here, one there, here, so, right? So it is bordering so many others. Now, whichever it borders has to be a piece, right? Isn't it? Because it is some other element, say R prime, and what was the definition? That where we have a common subword, and this is a common subword, isn't it? We cannot border with any other relator along a non-subword, right? So we essentially border along subwords, and if we border with some other relator, we are bordering along common subword. So this subword, this face, this side of this face R is a common subword and is a piece. Now you see that if you satisfy the condition CP, what does it say? It says that no element in R is a product of less than P pieces. So here, if all these are pieces, then how many edges, how many sides should this face have? It should have at least P sides, right? Because otherwise it will violate this condition. If I have, say, P minus 2 sides of this face giving me R, then that will violate the condition CP. So pictorially, this is what it means, that if I have a diagram like this, a Van Kampen diagram, which has this interior face. Interior means it's not bordering the boundary of this diagram. If I call M, then this delta M is P by our notation, right? So P is the boundary level. So P is the boundary level, and that is so F of P is W, right? So, and a face we will call interior face if its boundary does not intersect the boundary of the entire diagram. This is not an interior face because the boundary of this face intersects the boundary of the diagram. This is an exterior face. Now, we cannot say anything in particular about them because we don't know what these subwords are. We cannot say they're piece or anything, but these are definitely pieces. The boundary, the sides of the interior faces are definitely pieces, and we can say by this condition that there has to be at least P of them.
Yeah, one question.
Yes.
So can the piece, the length of the piece, can it be greater than one? I mean,
Sorry.
Length of piece. What example you have shown? It is
Yes. It can definitely be greater than one. I mean, very long it can be. We will come to such examples. I mean, not too difficult to construct, but we can. And answer is yes. It can be greater than one. And one other thing we can observe here, that you see here it satisfies C8. This group satisfies C8 because all these. So the relators have length 8, and the pieces are length 1. So it satisfies C8, but it satisfies what? C prime 1 by 7. So that's what it is saying. So you see that if you have C prime 1 by n, so you know that your pieces are less than, say, 1 by n of your total relator length, right? So now what you can say is that if so your pieces less than 1/n of R, right? That means if you want to write down R as a product of pieces, suppose you have an interior face like this. So how many of them will you need? If you take n of them, so n will be less than the length of R, n of u, right? So you need at least one more, right? Right? So if your presentation satisfies this, you need at least one more. That is also not sure, but you need at least one more. You don't know, you can't say that this is equal to this is not clear. I mean, you don't know, it may not happen. or that this is greater than or equal to R. So none of these things are true in general, but you can say that at least n plus one of pieces are required to write down R. So that says that C prime 1 over n implies C n plus 1. So that's sorry.
Yeah. So one more question. Uh,
Yes.
so is this definition of CP presentation invariant? I mean, if I change the presentation, so it may be some other CP prime also, right? That can be also possible. Same group with different presentation. This
Yes.
CP will also change, right? CP might get changed to CP prime.
Yes, you don't need to have the same coefficients for the small cancellation conditions if you change the presentations.
So this P will change to some other P prime. That you are saying, right?
Yes, but largely they will be invariant. We will come to that.
Okay.
Okay. So there is another condition that we want to talk about. It is called TQ. So what it says essentially is a presentation satisfies TQ condition if for say L of them, L relators, if we have say L is greater than or equal to 3 and less than Q, etc. And Ri is not equal to Ri plus 1 inverse. What do I mean by that? Say Ri not equal to Ri plus 1 inverse in the sense you do not have cancellations here. I mean, full cancellations here. You understand? So essentially, I mean, if all of them, they are not equal. So Ri not equal, there is a little bit of, so I should write here I ranging from 0 to not 0, I ranging from 1 to L minus 1.
Yeah. This
So
R is
this
symmetrized, right?
symmetrized.
So then
So
Ri and Ri plus one inverse.
you see, it is not Ri inverse, it is Ri plus 1 inverse.
Oh, okay.
So what it is saying is Ri is this, so R4 is this, and what is R5? It is this, right? So R5 inverse is this, right? So if they are equal, what will happen? This entire part of the disk will become a line, right? So these two will come together. Suppose this is R6. Suppose this is R6. If R4 is equal to R5 inverse, what will happen? Suppose R4 is equal to R5 inverse. What happens? So if it is R4 equal to R5 inverse, then at least this part we can definitely see that they get cancelled, right? These parts. But if they are entire inverse of each other, then even there will be cancellation even on these parts, right? Right? Even on these parts. So this entire subdiagram will collapse. Do you see that?
Yes. Okay.
Right? So why is that condition I mean enforced? Because if this collapses, you see that what is getting reduced? If this subdiagram collapses, what is getting reduced? If this collapses, what is getting reduced? The number of edges that are attached to this vertex. That means the degree of this vertex, right? Right? So if this collapses, if say two of them are equal, then say you will have a fewer number of such diagrams, such cells glued to this point. So you'll have fewer number of edges attached to this vertex. So what it is saying essentially is every interior vertex of this Van Kampen diagram, of any Van Kampen diagram over such a presentation, if you take an interior vertex, so this is like an interior vertex. If you take an interior vertex, the degree of that vertex will be at least q. Okay. Okay. You see, in this case, again, we are going back to the presentation of z square. Look at any interior vertex, so, or any diagram like this. You see that the degree of that vertex is 4, any one. So this presentation satisfies T4 condition. And also you see that this condition, this presentation satisfies C4 condition. Why? Because the relators are product of 4 pieces, right? At least 4 pieces. Here they're product of exactly 4 pieces, but at least 4 pieces. So it satisfies C4 condition. So this presentation satisfies both C4 and T4 conditions. So anyway, reduced diagrams. So earlier we saw that when we start with a word, we how do we construct a diagram from that. Now I have kept a few things under the carpet here. I will come back to those things when it is absolutely required. But just in picture, I have given you the intuition why the picture should look like this, because it should have at least p pieces as a product. That means at least p sides, and this should have at least q degree should be at least q. So why are they like that? I mean, why is it so? So if the relation, if the presentation satisfies CP, then every interior face of a subdisk of M naught has P consolidated edges, right? So that is what we are trying to say. So why is that so? Oh, one thing I haven't mentioned is what is a consolidated edge. A consolidated edge is like this one. You see that we can have many edges like this, right? So like A, B, C, etc. Some generating. So this is a long word. So these are not edges, right? Essentially, they, I mean they are a concatenation of edges. So a consolidated edge is something when we extend an edge when the degree is 2. You see, at these points, the degrees are 2, right? So when the degree is 2, we extend it, and that we call a consolidated edge. So the interior face of a subdisk M naught, when it satisfies CP condition, has P consolidated edges, what we had drawn in the picture. So suppose this be a subdisk of the reduced diagram with 2 or more 2 cells. Okay, this is subdisk. So what we consider here is a tiling, a label tiling of this subdisk obtained from this diagram by consolidating edges. Consolidating edges means we are extending the edges whenever their degree is 2. Now, if X is an oriented edge of a face, so here by oriented edge we mean consolidated edge. So if X is an oriented edge of a face B in that subdisk D, you see that it has to be the level of that edge has to be a piece, just what we talked about some time back. Because if that is a consolidated edge, then and it is an interior face of a diagram, then there must be another face here, right? A 2 cell. So they are overlapping on this consolidated edge. And then by the definition of a piece, this consolidated edge or the label of this consolidated edge is a piece, right? So label is a piece, and the boundary delta B is the boundary level of the diagram of the face B. That is in R star, that is R in this case. So what does it mean? It means that delta B is a cyclic permutation of some relator, right? Because it's a two cell, right? So that must be in R star. I mean, in this case, R, we have assumed that it is symmetrized. So we already started with R satisfying CP condition. So that means this subword. So that means delta B is a concatenation of at least P sides, P consolidated edges. That means the diagram looks like that. And what about the other condition, TQ? Then Abhijita, how much more time do I have?
You have 3-4 minutes.
Okay. Okay, fine. So,
So another thing,
yes.
so in tutorial, if you want, you can explain it with this your whiteboard or some other way also. You want to draw a diagram.
Fine. So in the tutorial, Partho, I'll be present. Partho will mostly be drawing a few examples and diagrams. And I wanted to do curvature formula, but I'm a little out of time. So let's see. So this is the argument for essentially this picture, that we have at least T edges, at least Q edges coming out of that, coming out or going into that vertex, and that is following from the definition that at least one of the products has to be reduced if all these are not equal. Okay, so I leave this maybe. Is the definition clear, or should I repeat?
Once more, you can.
So so it is saying that if all these are not equal, then at least one of these products, R1, R2, R1, R2 means say this product you're forming, R2, R3, this product you're forming. So in this way, you go to say RQ, this is the last one. So RL in this case. So RL, R1, this product you're forming. So then at least one of these products is reduced without cancellation. Okay. One of these products, you don't have to cancel anything to reduce it. It's already reduced. Okay, that's what the definition says. Now if you
only
look at
one more.
this, sorry, yes.
So that presentation of fundamental group of torus Z plus Z. You said it is T4, right?
Yes,
Why it is T4?
if you see this argument, then you will understand, because that's a better way. This is not so good a way to understand TQ. This is the definition classically, but this is a better way to understand what TQ essentially implies. It says that you take any diagram for any W from the normalized from the normal subgroup generated by R, and then in that diagram you take any interior vertex. Okay, the degree of that interior vertex will be at least Q. Okay, and that is following from this. So in this case, you see here, you take any vertex, not only this. The degree is always 4, so it satisfies T4 condition. Okay. So Now you start with a presentation SR, and R satisfies TQ for some Q greater than or equal to 4. And suppose every interior vertex of a subdisk, you take a subdisk in M naught. So I think the main reason for taking an interior vertex of a subdisk is that you can actually go to a interior vertex. Otherwise, you can have exterior vertices, but it's not a big deal. And oh yeah, you can have degree 2 if you have exterior vertices. So M naught can have exterior vertices, just like one on the boundaries. Where did I draw? Yeah, this. If you have a vertex here, you see that this vertex has degree 2. So what this assumption is saying is that you just go to an interior subdisk, go to a subdisk, and by just like by passing to a subsequence here, it is like passing to a subdisk. You ensure that your vertices are all like that. So consider an interior vertex V in that diagram, in the tiling T, with x1, x2, xd oriented edges starting from the vertex V. Okay. Now what you do is, so essentially it is like, at this vertex V. Now for I from 1 to d minus 1, xi and xi inverse are the first and last edges of the boundary path pi of a face bi. What it means is that this is an interior vertex, right? So you have, say, face b1 here, whose this is the base point, suppose. Then you're starting along this x1, and you're coming back along x2, right? So this is a two-dimensional diagram. So if you go like this, you have to come back like this, right? So that is what they're saying, that xi and xi plus 1 inverse. So xi and xi plus 1 inverse. So xi this way. So xi and xi plus 1 inverse, they are the first and last edges of boundary bi of a face bi. So this is the face b1, is the first and last edges of the boundary path. Okay, pi. So let Ri be the level of the path pi. So Ri is the level of this path, right? So B1 is the face, and its level you call Ri. Okay, so Ri be the level of that path, and you see that none of the products, this R1, R2, R2, R3, RD, R1. So R1 is this, and this is R2. Suppose it is like that. So this is R2, just like this. This is R3, and so on. So none of these products, these are freely reduced, right? Right? Yes or no? Do you understand? None of these products are freely reduced. If they were freely reduced, then you would not have these common portions, right? These edges.
Right.
Is that clear? So none of them are freely reduced because they are consecutive related. I mean, those faces B1, B2, BD, they are all put together at one vertex. They are all neighboring. I mean, consecutively neighboring, right? So none of these consecutive products, they are freely reduced, because if they were, then there will be a situation like this, right? So this will be R1 and this will be R2, right? So in that case, you have a freely reduced product. If you have R1 this, R2 this, then R1, R2 is freely reduced, right? Because you do not have any cancellation, correct?
Right.
But in this case, it is not the situation. So none of them are freely reduced. So you satisfy this, right? So none of them are freely reduced. So R1 inverse is not equal to R2, RD inverse is not equal to R1 as the diagram is reduced, because you have already started with a reduced diagram. We have started with a reduced diagram, M naught. So that we can always do, right? Just like a diagram of this type. So now we know that this presentation satisfies TQ condition, right? So what does that mean? That means we have all the requirements satisfied, and TQ says that it will have, and we see that we have degree greater than or equal to Q, right? What would have happened if a situation like this was there? See that, I mean, we cannot say, so at least one edge is going out or coming in there. I mean, at least it is doing both, in fact. So we have two edges clubbed together for this for this product R1 R2. So it satisfies the definition of TQ, and hence the degree has to be at least Q. So shall I continue 5 more minutes, or we will come back for the...
You want to explain with examples, right?
Yeah.
Okay.
So,
All right.
so shall I go ahead now?
Yeah, yes.
Okay. So some of these I have already talked about. You see, this one, it needs no further discussion, I guess. So we understand this. Now, if we have a group which is the fundamental group of genus G surface, we see that the relator is this one, and the relator is it's a 4G minus 4. It's a 4G gone, right? Right. So it's a 4G gone, and like in this situation, we had an octagon, and what were the pieces? The pieces were still the edges. Here we have a 4G gone, and what are the pieces? Just look at the relators. If we have a genus 3 surface, what do we have? Say A1, B1, A2, B2, A3, B3, right? So A1, B1, A1 inverse, B1 inverse, A2, B2, A2 inverse, B2 inverse, A3, B3, A3 inverse, B3 inverse. None of them, I mean, are nowhere we have a word whose length is a subword whose length is greater than 1, which is appearing at two distinct places, which can satisfy as a piece, right? So still the pieces are edges of these 4G gone, right?
So
Right.
here we
So
have
the,
to take two R1 and R2. In
sorry,
this example,
this
genus,
one,
genus G. Sorry.
genus G, yes.
So you have to take two R1 and R2, right?
Yeah. So even if you have only one relator, right? So R1 and R2 means different cyclic permutations.
Sure.
It's a one relator group, right?
This is the one.
So you take two different cyclic permutations, just like this, right?
Okay.
Right. So now, what are the common subwords on which their boundaries can overlap?
No, it just no. So in this thing,
What was your question? Sorry.
there is a single relator group,
Yes.
and if you go back to the definition,
Okay.
C prime,
Definition slide.
C prime lambda.
C prime lambda. Yeah.
So here, what is your this R?
What is my R?
So if it is single related thing, what does it mean?
Yes. See, R is what? Here, R is the symmetrized relator set of relators,
Okay.
right? And for all elements from that set of symmetrized relators, this should happen, right?
Okay. So then that one relator group corresponding to
Yes.
that thing, that is not symmetrized, right? You have to make it symmetrized, right? No?
Yeah, so essentially when we are considering the conjugates, see, when it may seem like one relator, right? But suppose your base point is here. Suppose your base point is here. And let's take here. Let's take here. A, B, A inverse, B inverse, C, D, C inverse, D inverse, right? So if I take the base point here. Now, if I take the base point, say here, suppose I want to start from this. A cyclic permutation means what? I can start from any vertex on the
No,
relator.
that I understand. What I'm saying is that in this collection R, you have to throw more related. So you have to permute.
No, we are not essentially. We are not. Yeah, what I'm saying is, I have other cyclic permutations of the same relator. We are not throwing in more relators because they are anyway just like a conjugate of the same thing, right?
They will represent the same group, but
Because this the other symmetrized thing we are talking about, if I want to start from here, cyclic permutation means I can start from any of them, right? So if I want to start from there, maybe I will take this path, okay? Then I will trace the entire relator, and then I will come back this. What is happening? I'm getting the same thing, right? Right? So we are not getting new relators. By taking a symmetrized set of relators, we are not getting new relators.
okay.
We are just taking in all the because of the ease of stating these conditions. Because you see that I have to be able to write it. I have to be able to write it this way. So how can I write it this way, keeping the U in the beginning, if I don't have the other options?
No. Here, when you have defined P's, then you have taken R1, R2 in R, right? Now R is
Yes.
single relator, right? So
Not
then,
single relator in the sense, not a single relator. It is the collection of all cyclic permutations.
yeah,
See
that I'm
here,
saying. You have to extend this R, so then you can do this thing.
yes. So R is symmetrized if all R and they are cyclically reduced, all R here are cyclically reduced, and distinct cyclic permutations of R and R inverses are all in capital R.
Yeah, right.
Okay. But essentially they are all the same. If I have a one relator group, they are essentially, all of them are giving me the same relator, because I can write them as a conjugate, a different
Right. Yeah,
cyclic permutation,
that's true.
right? Okay. So so this is clear, right?
Yes.
Right. Fine. So if that is clear, then how many edges do we have here? We have 4G edges on the relator. And what can become a piece? A piece is only an edge of that, nothing more than that. So I can write, if U is a piece, then I can write this. Sorry. I can write this, right? And that implies I can write. Sorry. So it satisfies this small cancellation condition, and also from the same thing you can see that it satisfies C4G condition, right? So it's a C prime 4G minus 1 and C4G group. Okay. Now this condition, this example I'm leaving for the time being. I'll come back to this later. Let's look at this example. Here you have this relator a1 square, a2 square, ak square, right? Now in a cyclic permutation, if you write it cyclically, so what are the possible pieces? There is a question. If we know what the possible pieces are, then we can measure I mean whether it's small compared to the relator or not. But what are the possible pieces here? You write it as a1 a1, a2 a2, and so on, right? ak ak. So it says that ai's are the pieces but not ai squares. Do we understand that? That ai's are the pieces but not the ai squares? Because for AI, I have two different presentation, different elements like this. If I take AI square, I do not have two distinct elements like this, such that it gives me this AI square in the beginning, and the V1 and V2 are not the same. But if I take AI, say I take A1, I can take A1 times A1, A2, A1, I can take A1 times A1, A2 square, A3 square, A K square, right? And I can also take A1 times A2 square, A3 square, AK square A1, right? Under cyclic permutation, right?
Yes.
So if I write it this way, I have two A's here. Once I will start from here, and once I will start from here. So the two other words, V1 and V2, they will be different, right? So I have two different ways this subword is appearing in my symmetrized relators, right? So and for no other subword that is happening, right? Is not happening for any other subword. So what are the pieces in this case? Pieces are only AIs. Now, if that is the case, how many of, what's the length of this? What's the length of the relator? It's 2K. And what are the only possibilities for the pieces? The AIs, right? So again, the same way I can say that the pieces is this, and hence it is this. Okay, so and in this example, the last one, what we can see is it's a very long word, say a b square, a b cube. So I'm increasing the powers of b but keeping power of a same. So I'm writing different powers of b interjected by a. So I will finally have, say, a to the 97, b to the 97, a, b to the 98, a, b to the 99, a, b to the 100, right? So that is how the relator will look like. Now, what are the pieces here? Can we see?
A is a piece.
Fine.
And
See,
if
when we will be trying to test these conditions, should our focus be on smaller pieces or bigger pieces?
we can get
Bigger.
bigger pieces also.
Yeah, so our focus will be entirely on the bigger pieces, because if I can say this that it satisfies this condition for larger pieces, then it will satisfy for say other smaller ones as well, right? So having said that, what can you figure out what the largest piece in this situation will be? Some subword which has two different appearances, at least two different appearances.
I can get two at least here. AB. If I move AB to the last, right?
But can you find larger pieces? That's what I asked.
I can bring B power 100 in the front, right?
You can, but do you have a second appearance of B to the 100?
I'm not saying B to the 100, but some lesser than some 100.
Yeah, so my question is, can we see some piece somewhere hidden in this expression? This is a one related group, right? So whatever pieces I have, they must come from this relator, from
B
different
power
cyclic.
99 will be.
Yes, but can you find a larger one? See, uh, if we look at this, say b to the 97, a b to the 98. You see, if I write this as b to the 98 as b times b to the 97 a, then b to the 99 as b to the 98 b, then a, then b to the 100. Then I have another appearance of this here, right? B to the 97 a, b to the 98. And by the same argument, if I look at this, b to the 98 a, b to the 99, you can write this as b to the 99 as b times b to the 98 a, b to the 100 as b to the 99 b. And you see that it appears again here, right? So can we find a larger piece? Can we find a larger piece in this word, in this relator? No, right? Do we have a larger piece? We can consider b to the 99, a, b to the 100, but that appears only once, right? B to the 99, a, b to the 100 appears only once. So this is the largest piece that we can have possibly, b to the 98, a, b to the 99. So what's the length of this piece? It is
198.
198, right? And what is the length of the relator? Say A appears 100 times, so 100 plus B appears n into n plus 100, right? So
5,000.
what would, so something more than 5,000, right? And what is the length of this? Something less than 200, right? So we can definitely say that the piece, length of the piece is less than 120 times the length of the relator. right? So 1 over 20 times the length of the relator, that it satisfies in this case. So this group satisfies the C prime 120 1 over 20 small cancellation condition. We can check this way. So these are few preliminary examples that we have discussed. Now I will briefly state this result to the proof, and this is a very important result in the entire geometric group theory. This is a very important result. So this is one of the most famous small cancellation construction that we have. What it says is that suppose lambda is a scalar greater than 0, G is a group, finitely presented group with this presentation. Then we have a short exact sequence in the sense that we can construct a group gamma, which is a small cancellation group. We can construct a small cancellation group gamma such that G is a quotient of that group. G is a quotient of the group gamma, and this is the normal this is the kernel. So this is a normal subgroup of this group. So now we have this exact sequence. Now, what is the most interesting thing here is that I haven't specified any lambda. Lambda was any real number, positive. So I can take lambda to be as small as I wish. Given that lambda, whatever be the presentation of G, it is just required to be a finitely presented group. Now, whatever be lambda, I can construct a finitely presented C prime lambda group gamma such that G is a quotient of that group gamma. Now, one of the main things that we will be proving in this mini course is that gamma is a hyperbolic group. What we will be proving is if we have a C prime 1/6 presentation, then that group is Gromov hyperbolic. And so if lambda is anything less than 1/6, which it can be because lambda is arbitrary. So if I take a lambda to be say 1/10, then I know gamma modulo the result that I just stated, that C prime 1/6 group will be Gromov hyperbolic. So then definitely a C prime 1/10 group will also be Gromov hyperbolic. And this theorem says that I can see any given group, any given finitely presented group G as a quotient of a small cancellation group, a Gromov hyperbolic group in particular. So, and also this is also important that the kernel is finitely generated. So I mean, it may have had happened that infinite kernel gives us this, but no. So even the kernel is quite well behaved, a finitely generated kernel. I mean, well behaved in that sense, gives me G as a quotient, and the proof is just saying that I take the generating set of G, generating set and the relators of G, and I sort of fiddle around with the generators and relators of that group to define new relators. I just extend the generating set of the group and define new relators. So then I construct that group gamma with those new generating set and relators. And what I do is I take this map. I extend the generating set of the group G with these two elements, and I haven't mentioned here, I extend the set of relators to something else. That is the main construction. And then take this map. These generating elements of G are mapped to themselves individually, and the extra generators that I have taken, I'm sending the extra generators to 1, both of them to 1. So this gives me an onto homomorphism from gamma to G, right? And that the kernel of that homomorphism is finitely generated. And what is the kernel? The kernel is this, and hence I get the finitely presented group G as a quotient of a C prime lambda group, and we have C prime lambda groups are hyperbolic groups. So I get a arbitrary finitely presented group G as a quotient of hyperbolic group, and that is a phenomenal result in the sense it gives us something called SQ universality, that I have arbitrary quotients, right? So G can be seen as a quotient of, say, just you keep changing lambda, you can see G as a quotient of so many hyperbolic groups, in particular small cancellation groups. And I will also mention at this point, but I don't know whether I will be able to give an outline at least of the proof of the fact that I don't know whether Canon-Thurston map has been discussed in this mini course so far. Vijita, has it been discussed?
The definition has been given.
Of Canon-Thurston map?
Yes.
Okay. Okay, so it was a question, long-standing question asked by Mohan Maharaj, that whether Canon-Thurston maps always exist in the proper context when it is defined. I mean, when it can be asked. So that question was answered negatively by Baker and Riley, and the construction is again by through some small cancellation group, very much closely related to this type of a construction. So the idea of the proof is quite different from this proof, but again, a very concrete small cancellation presentation has been used to disprove that, to answer that question in the negative. So okay, fine. So I will stop here. It's already 4. I'll stop for today here. Vijita, what is the plan with the?
After 15 minutes, we can.
Okay.
Okay.
Okay. So fine. So Partho will be discussing examples and diagrams, etc. And should I be? I'll be present, right?
Yeah. Yeah. Sometime, please.
Fine. Okay. Thank you. Any question?